Lake Tahoe appears calm, almost unnaturally stable, a vast inland body of water framed by mountains that seem immovable on any human timescale. Yet beneath that surface lies a system defined not by stillness, but by motion that is slow, accumulating, and occasionally violent. The question is not whether the basin moves, but how it moves, and what happens when that motion transfers energy into water instead of just rock. Could a lake, far from any ocean, generate waves powerful enough to resemble a tsunami? Could faults hidden beneath hundreds of meters of water displace enough volume to send surges racing toward the shoreline? And if such an event has already happened in the past, what does that imply about the future? Lake Tahoe occupies a tectonic setting that is far more complex than its scenic surface suggests. It sits at the boundary between two major geologic provinces, the relatively rigid Sierra Nevada block to the west, and the actively stretching Basin and Range province to the east. This boundary is not a simple line, but a transition zone where the Earth's crust is being pulled apart, fractured, and dropped downward along normal faults. The basin itself is the direct result of this extension, formed over millions of years as sections of crust subsided relative to the surrounding mountains. The lake's origin is therefore inseparable from faulting. Rather than being carved solely by glaciers or volcanic activity, the basin formed when tectonic forces caused a large block of crust to collapse downward, creating a deep depression that later filled with water. This structural origin is critical because it means the same processes that created the lake are still active. The Sierra Nevada continues to rise, while adjacent regions continue to extend and fracture. The basin is not a relic, it is an evolving system. The depth of Lake Tahoe underscores this tectonic history, reaching approximately 1,645 feet, or about 501 meters. It is among the deepest lakes in the world. That depth is not uniform, but shaped by steep underwater slopes and fault scarps, features that are not only evidence of past movement, but also potential sites of future instability. These submerged slopes, in some areas, descend sharply enough to behave like underwater cliffs. Beneath the lake, multiple active fault systems intersect and overlap. Among the most significant is the West Tahoe Dollar Point Fault Zone, which runs along the western margin of the basin and continues beneath the lake itself. This fault is not isolated. It is part of a broader network that includes additional structures on the northern and eastern sides of the basin. Together, these faults define the geometry of the lake floor and control how stress accumulates within the crust. What makes these faults particularly significant is their configuration and potential for synchronized movement. Some segments appear to be linked, meaning that rupture along one portion could propagate into another, increasing the total length of fault that slips during an earthquake. This has direct implications for magnitude. A longer rupture typically corresponds to a larger earthquake, and in the case of Lake Tahoe, modeling suggests that earthquakes in the magnitude 7 range are plausible. The recurrence interval of such earthquakes spans thousands of years, but the geological record indicates that the system is not inactive. Evidence suggests that major events occur roughly every 2,000 to 4,000 years, with the most recent large rupture on at least one major fault occurring more than 4,000 years ago. This places the system within a time frame where accumulated strain may already be significant even if no immediate event is imminent. The presence of water fundamentally alters the hazard profile of these faults. In most tectonic settings, the primary concern is ground shaking and surface rupture. In Lake Tahoe, the overlying water column introduces an additional mechanism, displacement of water mass. When a fault moves beneath the lake, it can shift the lake bed vertically, pushing water upward or allowing it to drop. Even a displacement measured in a few meters can translate into a large volume of water being suddenly redistributed. This process is analogous to how oceanic tsunamis are generated, but with important differences. In the ocean, tsunami waves often travel long distances before amplifying near shorelines. In a lake environment, the water is relatively shallow compared to the wavelength of the waves, meaning that the energy remains concentrated within the basin. Instead of dissipating across an ocean, the energy reflects off the basin boundaries, potentially creating complex wave patterns and repeated surges. One of the most significant mechanisms for generating large waves in Lake Tahoe is not just fault displacement, but underwater landslides triggered by seismic activity. The steep underwater slopes, combined with unconsolidated sediments deposited over thousands of years, create conditions where shaking can destabilize large sections of the lakebed. When these materials suddenly collapse and move downslope, they displace water rapidly, producing waves that can exceed those generated by fault movement alone. Evidence for such events exists within the sedimentary record. Studies of the lake floor have identified displaced sediment layers and scarps that indicate past events where large masses of material shifted abruptly. In at least one instance, a scarp approximately 10 meters high suggests that significant force was applied to the lakebed, likely displacing water and generating waves consistent with a tsunami-like event. The geometry of the lake amplifies this risk. Lake Tahoe is not a uniform basin. It has irregular shorelines, depth variations, and steep gradients that can focus wave energy towards specific areas. Modeling of possible events indicates that waves generated on the western side of the lake could travel toward the northeastern shoreline, impacting communities across the basin. The direction of such waves depends on the location and orientation of the source disturbance, whether it is fault movement or a landslide. Wave heights in these scenarios are not negligible. Simulations suggest that a magnitude 7 earthquake could produce waves reaching approximately 30 feet or around 10 meters in height under certain conditions. Even more moderate events could generate waves on the order of 20 feet or roughly 6 meters, depending on the size and speed of the triggering landslide. These values place inland tsunami scenarios within a range capable of causing significant damage to shoreline infrastructure. Unlike coastal tsunamis, which may provide some warning time as waves travel across open ocean, a lake-generated wave would arrive quickly. The limited size of the basin means that wave travel times could be measured in minutes rather than hours. This reduces the available window for response and increases reliance on immediate recognition of the triggering event, such as prolonged ground shaking. Another factor that distinguishes lake tsunamis is the phenomenon of seiching. Rather than a single wave, the water may continue oscillating back and forth across the basin, similar to water sloshing in a container. This can result in multiple surges impacting the shoreline over an extended period, complicating evacuation and response efforts. The energy introduced into the system does not simply dissipate after the first wave, but can persist, reflecting between basin margins. The risk is therefore not limited to a single impact, but includes a series of water movements that can continue for hours. In enclosed basins like Lake Tahoe, this behavior is governed by the shape and depth of the lake, as well as the initial distribution of energy. The result is a dynamic water surface that may rise and fall repeatedly, with varying intensity depending on location. The structural complexity of the fault systems beneath Lake Tahoe further complicates hazard assessment. The faults are not simple, continuous planes, but segmented structures with varying orientations and slip characteristics. Some segments may move independently, while others could rupture together in cascading events. This segmentation influences both the magnitude of potential earthquakes and the distribution of displacement across the lakebed. In addition, not all fault movement produces the same type of displacement. Vertical motion is the most efficient at generating waves, but even primarily horizontal movement can contribute indirectly by triggering landslides. The interaction between different fault segments and the material properties of the lakebed determines how much water is ultimately displaced. The presence of volcanic features in the region adds another layer of complexity. Past volcanic activity, including the formation of lava flows that help seal the basin, indicates that the area has experienced multiple geologic processes over time. While current volcanic activity is not the primary driver of tsunami risk, the legacy of these processes influences the structure and composition of the basin, including the stability of underwater slopes. The surrounding topography also plays a role in amplifying or mitigating wave impacts. Narrow bays can concentrate wave energy, leading to higher local amplitudes. Conversely, broader shoreline areas may experience more distributed effects. The interaction between incoming waves and shoreline geometry determines where damage is most likely to occur. In considering the full hazard profile, it becomes clear that Lake Tahoe represents a convergence of multiple risk factors: active faulting, steep underwater slopes, deep water, and a closed basin that can trap and reflect energy. Each of these elements alone would warrant attention, but together they create a scenario where relatively rare events could produce disproportionate impacts. At the same time, probability must be distinguished from possibility. Estimates suggest that the likelihood of a magnitude 7 earthquake occurring beneath Lake Tahoe within a 50-year period is on the order of 3 to 4%. This places the risk in a low probability category on human timescales, yet the geological record confirms that such events have occurred and will occur again over longer intervals. The key issue is not frequency alone, but the nature of the outcome when such an event does occur. A fault rupture beneath hundreds of meters of water introduces a chain reaction. Ground movement leads to water displacement, which may trigger additional mass movement, amplifying the initial disturbance. The result is a coupled system where solid earth processes and fluid dynamics interact in ways that are not immediately visible from the surface. This interaction is what defines the concept of an inland tsunami in Lake Tahoe. It is not a direct analogue of oceanic events, but a distinct phenomenon shaped by the constraints of the basin. The waves may be shorter in wavelength, the travel distance is smaller, and the timescales compressed, but the underlying principle remains the same: rapid displacement of water generating waves capable of transporting energy across the surface. The implications extend beyond immediate shoreline impacts. Infrastructure, marinas, roads, and low-lying developments around the lake are all positioned within zones that could be affected by sudden water level changes. Even a rise of several meters can inundate areas not designed for such events, particularly if accompanied by repeated oscillations. The evolving understanding of Lake Tahoe's underwater faults has been driven in large part by advances in imaging technology. Sonar mapping and seismic profiling have revealed structures that were previously hidden beneath sediments and water. These methods have transformed the perception of the lake from a stable landscape feature into an active tectonic environment with measurable risk. What remains uncertain is not whether the mechanisms exist, but how they will interact during a future event. The distribution of stress along the faults, the stability of underwater slopes, and the precise geometry of potential ruptures all influence the outcome. Each factor introduces variability, making precise prediction difficult, while still allowing for scenario modeling based on known parameters. As research continues to refine these models, the picture that emerges is one of a system capable of producing significant localized water disturbances under the right conditions. The combination of fault-driven displacement and potential landslides provides multiple pathways for wave generation, each with its own characteristics and possible impacts. This is the underlying reality of Lake Tahoe, a landscape defined not just by its visible beauty, but by the hidden structure beneath it. A basin formed by faulting remains governed by faulting, and the presence of water transforms that geologic activity into something that can move across the surface with force. The question is not whether such processes are active, but how their eventual release will manifest when stress accumulated over thousands of years is finally discharged. The scenario begins not with visible water movement, but with a rupture deep beneath the lakebed, where accumulated stress along one or more fault segments is suddenly released. A section of the crust shifts by several feet over a matter of seconds, equivalent to a displacement of a few meters, and that motion is transferred directly into the overlying water column. At the same time, the shaking propagates outward, radiating through the basin and into the surrounding mountainous terrain. The ground itself does not need to break the surface to initiate a significant event. The changes occurring beneath the lake are sufficient to set the system in motion. Within moments, the water above the area of displacement is forced upward or allowed to subside, depending on the direction of fault movement. This vertical shift, even if measured in only a few meters, displaces an enormous volume of water due to the size of the lake. The initial disturbance spreads outward in all directions, forming a series of waves that begin traveling across the basin. Unlike oceanic tsunamis, where wavelength can stretch across hundreds of kilometers, these waves are constrained by the lake's dimensions, resulting in shorter wavelengths but still carrying substantial energy. At the same time, the shaking destabilizes steep underwater slopes along the margins of the basin. Sediments that have accumulated over thousands of years begin to fail. Entire sections of the lakebed can detach and slide downslope, accelerating under gravity. These underwater landslides introduce a second, often more powerful source of displacement. As large masses of material move rapidly, they push water aside, creating waves that can merge with or amplify the initial waves generated by fault movement. The interaction between these two processes, tectonic displacement and mass movement, determines the overall character of the event. If a landslide occurs near the same time and location as the fault rupture, the resulting waves can combine, producing higher amplitudes than either process would generate alone. In some modeled scenarios, this combined effect is what drives wave heights toward the upper estimates of around 30 feet, or roughly 10 meters. The propagation of these waves across Lake Tahoe is influenced heavily by the shape of the basin. The lake's floor is not symmetrical, and its shorelines vary between steep, confined bays and broader, gently sloping areas. As waves travel, they interact with this geometry. In narrower sections, energy can become focused, leading to localized increases in wave height. In wider areas, the energy spreads out, reducing amplitude, but increasing the area affected. Travel times across the lake are short. A wave generated near the western margin could reach the eastern shoreline in a matter of minutes. This compressed timeline means that the interval between cause and effect is minimal. Ground shaking may still be occurring when the first waves arrive at certain locations. There is little opportunity for organized evacuation. The response window is effectively immediate. As the waves approach the shoreline, they begin to shoal, increasing in height as the water depth decreases. This process can transform a relatively modest wave in deeper water into a much larger surge at the shore. The degree of amplification depends on the shoreline gradient. Steep shorelines may experience abrupt, powerful surges, while gentler slopes may see water advancing further inland with somewhat lower peak heights, but broader inundation. The first wave is not necessarily the largest. Due to the enclosed nature of the basin, energy reflects off opposing shorelines and returns, interacting with incoming waves. This creates a pattern of interference that can produce multiple surges of varying size. The phenomenon of seaching becomes pronounced, with the lake oscillating back and forth. Water levels rise and fall repeatedly, sometimes for hours, as the system gradually dissipates energy. Certain locations around Lake Tahoe are more vulnerable than others due to their geography. Low-lying areas, marinas, and developed shorelines are particularly exposed. Infrastructure built close to the water's edge may be subjected to rapid inundation, followed by strong backwash currents as the water retreats. This back-and-forth motion can cause cumulative damage, undermining structures and eroding shorelines. In areas where underwater landslides originate, the effects can be even more severe. Waves generated close to shore can arrive with little to no delay, and their steep fronts can result in higher impact forces. These localized events may not affect the entire lake uniformly, but can produce intense conditions in specific zones. The cascading nature of the hazard becomes evident when considering secondary effects. Debris mobilized by the waves, including sediment, vegetation, and human-made objects, can increase the destructive potential of the water movement. Repeated surges can transport this material back and forth, compounding damage to structures and complicating any immediate response efforts. Another critical factor is conditions of darkness or reduced visibility. If such an event occurs during hours of darkness, the ability of people to recognize the risk and respond appropriately is diminished. Without clear visual cues, the initial awareness may rely entirely on the sensation of ground shaking, which may not immediately be associated with a water-based threat in an inland setting. Seasonal variations can also influence outcomes. Higher lake levels increase the baseline from which waves build, potentially allowing surges to reach further inland. Conversely, lower water levels may expose more shoreline, but could alter how waves break and dissipate. Snowpack, soil saturation, and other environmental factors may affect the stability of slopes both above and below the waterline, influencing the likelihood of landslides. Despite these complexities, the underlying sequence remains consistent. Fault movement introduces energy into the system, ground shaking triggers additional mass movement, and the resulting water displacement propagates through the basin as a series of waves. The enclosed nature of Lake Tahoe ensures that this energy remains largely contained, leading to repeated interactions between waves and shoreline. Modern modeling efforts attempt to quantify these processes, simulating different combinations of fault movement, landslide volume, and basin geometry. While uncertainties remain, these models consistently indicate that inland tsunami scenarios in Lake Tahoe are physically plausible and capable of producing significant impacts under the right conditions. If you found this breakdown valuable, make sure to like, share, and subscribe, and tap that hype icon to help this video reach a wider audience.